Exponential functions do have some good applications in things, usually called growth and decay is one of the biggest applications, and these formulas aren't always fun to work with, so it's one reason why you don't see them a lot being used in everyday life, but if you're in certain businesses you would be using them. So the general exponential growth is y equals capital C times the quantity 1 plus r, close your parentheses, to the t, where y represents the final amount, c represents the initial amount, r represents the rate of change, again you have to change it as a decimal, and t represents the time. So we're going to use that formula and solve a problem using that then. So we have to take these things and put them in that formula. So again, the formula is y equals c parentheses 1 plus r all to the t. So the first thing says write an equation. Well, there were 294,105 females participating in high school sports in 1971. I would be one of those. Since then, that number has increased an average of 8.5% a year. I'm not sure where these statistics came from, but they came out of the algebra book that I was using, so I'm not sure if they've been updated or not. So write an equation to represent the number of females participating in high school sports since 1971. So C, remember, was the initial, which was the 294,105. And then it's going to be 1 plus, how do we write this as a decimal? 0.085. And we just wanted a general equation. They're not doing a specific time, so it would be t. So if we just simplify that, it's going to be 294,105 times 1.085 to the t power. So that would be our equation. And now use that equation to calculate. So again, let me write down the equation for us. So y equals 294,105 times 1.085 to the t. So, excuse me, 1971 to 2001 would be 30. So we're just going to substitute a 30 in here for the t. So I want to just go ahead and do that instead of writing the equation over again. And do the math. Again, this is why it's nice to have a calculator to do this, because if you want to take 1.085 to the 30th power, you're going to get 11.5 blah blah blah. So this is really 11.5. I'm just going to leave it in the calculator, but it does go on around 11.6. Then times 294,105, you're going to get 3399339, and then the decimal. So if we were rounding, it's a 0.5, so I guess we should round up to make this 40. So 3,399,340, probably ought to label, females participating in sports in 2001. And again, if you want to compare today, I don't know if that increase is the same or if it's leveled off. I really don't know. So that's an example of using the exponential growth. Another formula that has exponents in it is going to be the one used for compound interest. So here's the formula. A represents the amount of the investment. P is the principal, which is the initial amount. R represents the annual rate of interest, expressed as a decimal. N represents the number of times that the interest is compounded, so that means added on each year. And T represents the number of years that the money is invested. So again, lots of letters there that you have to know what they mean. And you can just put them in the formula and go from there. So again, the formula is A equals your principal. 1 plus r over n all to the t. So this is a kind of an old problem. Native Americans received $24 for Manhattan in 1626. So that would be the initial principal that we're starting with. If it had been invested at 6% a year, compounded semi-annually, so we have our 1, so 6% would be 0.06. Semi-annually would be how often? 2 years. How much money would there be in the year 2026? So, oops, I think I Forgot part of the formula on that last part. So this is supposed to be NT. So in that case, it's going to be 2 times, and that would be 400 years. 2 times 400. And so then, again, it's just doing the calculator and taking all that and doing the math. So this is going to be 24 times 1. This would be 0.06 is going to be 0.03 when you take half to the 800. Take 1.03 to the 800 and then multiply, and you're going to get 4.47 times 10 to the 11th, which would be 447 000 dollars. So $447 billion, I believe. Then we have exponential decay, kind of the opposite of growth. You see the formula looks very similar, except instead of adding, you subtract the rate. So, and again, the rate would be in decimal form. So let's see if we can use this problem, or this to find an answer to a problem. Again, let me write the formula here at the top so we'll have it. Y equals C times the quantity 1 minus R all to the T power. Yeah, it's supposed to be a T there. So, 1950, the use of coal by residential and commercial users was 114.6 million tons. Many businesses now use cleaner sources of energy. As a result, the use of coal has decreased by 6.6% per year. Write an equation to represent the use of coal since 1950. So again, we're going to start with Y equals the initial amount, 114.6 million. 1 minus, again, write it as a decimal point, 0.066, all to the T power. So if we simplify this, it's really going to simplify into, let's write it up here, 1y equals 114.6, guess that's right, times 0.934, all to the T. So that would be the equation, and then if it says estimate using that equation, we're going to replace the T with a 65, so it's going to be 114.6 times 0.934 to the 65. And if you do that, you're going to get 1.35 million tons. So I do need to start the word million now since I didn't write that as million. You could go ahead and write it as that if you wanted to. And the last application is depreciation, which would be using this decay model, and very applicable when you buy a car. You know, they say it depreciates so much as soon as you drive it off the lot. So you're going to be using that same formula. Farmer buys a tractor for $50,000. If the tractor depreciates 10% per year, find the value of the tractor in 7 years. And so you can use something equivalent to this probably when you use your car. There's probably formulas out there. So the initial amount was $50,000. 1 minus 10% would be 0.1, and it's going to be 7. So 1 minus 0.1 would be 0.9. So you take 0.9 to the 7th power, multiply it by 50,000, you're going to get $23,914.85. So that would represent how much they should get out of their tractor. And there are taxes that have you take off depreciation and things like that, so that's probably a pretty important thing to know if you're doing depreciation of things.